Hello and welcome to today's episode of the Teardown Sessions from Crowd Supply. I am your host, Helen Leigh, and we have got a very exciting space-themed stream for you this week. Oh, very exciting. Okay, but before we bring our special guests on today, who have launched Oregon's first satellite into space successfully, which we're going to be hearing about during the course of the next hour, we're going to take a look at some of the stuff that is going on with Crowd Supply first. So let's have a look at what's new at Crowd Supply. So currently live, we've got 25 days left. It's actually reasonably recently launched. We've got RoAndy, which is a really cute open source rotary encoder with a hackable display there. So that's already raised $7,000. So if you want to support that, you've got 25 days left. Pretty neat little device. In the last 3 days, this is the last chance you have to support this one, we've got the Halo TD-XP-AH, which is the first open source 102.11ah scalable long-range Wi-Fi development platform, which you can see there with a nice purple gold there as well. We like that. And that has busted through its goal of nearly $8,000 and made it up to $22,000. We've got 3 days left. So if you want to get in on that, it's your last chance. Coming soon, we've got some really exciting things. First of all, I wanted to point you in the direction of a delightful little device that's about to exist called Beam Counter from Nick Poole. He has made this lovely little, it's just a device for counting cut reel SMD components. So it's just a lovely little device. I'm definitely getting one from my electronics workbench. Also coming soon, we have the Sharp RPI Kibo. I'm not entirely sure how to pronounce that. I'm sure I'll learn. But this has been blowing up on Twitter. It's a tiny little Linux computer with a QWERTY keyboard. Who doesn't want one of those? Also coming soon, we have an open source walkie-talkie from the folks behind SocoRad. And everybody's very excited about this one. The new Line SDR Mini has been teased and is soon about to be released. Now, I know a lot of people, lots and lots of people will be waiting for this one. So that's coming very soon. All right, now, before I wanted to bring our guests on, there are a couple more things I wanted to say. If any of you are actually located near Portland, which is where we are based, Crowd Supply, of course, we are hosting again a real life hardware happy hour, which is outdoors, of course, pandemic friendly. We're going to be geeking out in a bar on this coming Tuesday with some of our guests here tonight as well. So please do join us if you want to have a beer on a bar patio and come and hang out. That is happening. So finally, I wanted to give a big shout out to Qorvo, who have been sponsoring today's stream. We've got all sorts of wonderful giveaways from them. So thank you very much to Qorvo for sponsoring this stream. If you are developing anything that's using RF, specifically Qorvo's RF components, you should take a look at the Qorvo RF Accelerator program. That is a really great way of getting extra support for a Crowd Supply campaign if you are doing anything with Qorvo RF. So do check that out. All right, let's remove that. That's that spiel done. Now, finally, before we bring on my guests, I just wanted to, most of you already know how this works, but for those of you who are new to the stream, we always give away a box of mystery hardware in these very exciting lunch boxes. So inside this box, there's all sorts of interesting and mystery hardware. And the way that you win it is by commenting or asking questions. If you ask a question closest to the timestamp that I have on this post-it note, you will win our box of mystery hardware. Very exciting. And I can reveal that you'll also win a bunch of cool Qorvo swag, like these stickers, Qorvo all around you. We've got these lovely enamel pins as well. I like this one the best, I Heart RF. That one's a cool one. And then we've got these very swanky water bottles as well from Qorvo Insulated. So if you please do keep your comments and questions coming, and we will get that swag sent out to you. All right, without further ado, let's get on to the main part of the segment. And I'll try to use the mouse on my lunchbox, and that's not a shortcut. And let me add in my guests, and we will chat to them. Here we are. All right, so welcome to Emmy, David, and Andrew from PSAS. Hello. Good morning. Good afternoon, I suppose it is now. Hi, how are you doing?
Good, how are you?
I'm doing all right. I'm doing all right. It's a lovely day today, finally. So first of all, what on earth is PSAS for those of us who aren't aware, and what do you do? And tell us a little bit about your project and yourself, please.
Well, let me give the quick intro to the project, and then I'll let these guys introduce themselves. So Portland State Aerospace Society, or PSAS, which is the worst name ever, right, is a student group, an interdisciplinary student group at Portland State University, where we are right now. And we build rockets, liquid fuel engines, and satellites. And the thing that makes us particularly cool space hipsters is that everything we do is open source, like literally everything. And so we'll talk more about that, and we'll talk more about rockets and organs for satellite and the satellite kit that we built and all that kind of stuff. But these are the stars of the show because I just take credit for all the work that they do. So introduce yourselves.
Hi, I'm Emmy. I'm a senior mechanical engineering student at PSU, and I work on the structure team for our satellite, and I work on the recovery team for one of our rockets.
Yep.
Nice.
And then, hi, my name is David. I'm a senior electrical engineering student. I work on all of the bus aspects of the satellite, as well as some of the avionics for the rocket.
And my name is Andrew
Awesome.
Gruber. I'm a faculty advisor, I guess. I'm adjunct faculty here at PSU in electrical engineering, and help run the open source aerospace lab that we have here, and also do medical devices and consulting in industry for profit. This is
amazing. So tell me about OreSat. What has been going on with you, and what is it?
Well, okay, we have props. So
you have props. Excellent.
We have props. So we'll start simple because not everybody knows. So we're like we're really in the universe of satellites. So we may say stuff that other people don't know. So we'll give you hopefully some background.
Don't worry, I'll ask for clarifications. No acronyms on this.
So this is a CubeSat, and this is called a 1U CubeSat. Here, throw that up for the camera.
I'm going to highlight you.
Thank you. That is a tissue box size satellite. That's 3D printed, so obviously we're not going to fly that. That's just the sort of the size of it. This is a 2U, and you can tell that's about twice as big. That is so this is a 10 by 10 by 10 centimeter box. That's a 10 by 20 by 10 centimeter box, and this is a 3U. And just like servers have U's, right, a 1U or 2U server, CubeSats have U's as well. So we just launched a 1U CubeSat, which is, again, a form factor for nanosatellites, into low Earth orbit about a month ago. We built the satellite from scratch, which was stupid, and we'll tell you more about that. And it's currently working in low Earth orbit. It was beaconing for a long time. Now it's being quiet because as we get ready to get our ground station working. And shockingly enough, all of David and Emmy's works actually works.
So far,
That we know.
we have so a lot of people ask us, what does OreSat 0 do? And the answer is it's really a test. It's a test of all of the infrastructure that we're putting together for this CubeSat development kit, and everything from batteries to solar panels to everything. And we can go more into detail and technical detail on all those systems. But really, the cute mission statement that we use is, our mission statement is, do not catch fire in space, right? We want to make sure the thing actually works, and we want to make sure that we can hear it and that we can talk to it and that all those critical systems work, so that the next 2 satellites that we have on the docket will have a much higher chance of work. The technical name for this is technology heritage or flight heritage. So that's what we're doing right now, and that's what's in orbit right now is our first test satellite.
You want to show the engineering unit?
So you've got 2, you mentioned that you have 2 more satellites on the docket. Can you explain what that actually means? Do you mean you have 2 more slated to launch?
We have 2 more ride opportunities. We have a 1.5U satellite coming up and a 2U satellite coming up. One with NASA.
Tell me more about these ride opportunities. I mean, like, I've not put anything into space before, like most human beings. So how does this actually work? I know it. So you make your satellite. How do you actually get it up into space? So are you hitching a lift from NASA or what?
Yes and no. This is. I'll give you a little bit of background, and you guys jump in when you want to. So back in 2016, we started this project, and we started building a CubeSat, and we thought we need a ride to space, and so we went to NASA and we did something called the CubeSat Launch Initiative, or CSLI. And back in 2016, 2017, there's no way we would be able to afford to get to space. It was just too expensive and too hard. There wasn't enough opportunities. So we went to the CubeSat launch initiative. We said, hey, we're going to build this, again, 2U satellite, or maybe this is a better size because it's actually made of no metal. And we're going to do these really cool things. We're going to do this climate science mission, and we're going to do this big STEM outreach mission. And that's got ties to crowd supply that we'll talk about a little bit later. And so please fly our 2U satellite. And we were also the first group to do satellites in Oregon. And so they said, yes, absolutely, sounds great. And then we said, oh God, because we didn't really expect it. And so now we really have to build the satellite, and we really need to do this. And we've never done this before. We've done some rocketry work before that worked out really well. So we were all sort of hyped on ourselves that we could do satellites. And of course, satellites are much harder. And so we got this free ride to space from NASA.
Amazing.
However, it took us a really, really long time. It took us 5 years to build the satellite and do this and that. And while we were building it, we found out, by the way, this is part of the rocket.
Okay.
So
Wow.
I want to back up 1 second because we forgot one thing from the timeline. So part of the reason why we decided to go into CubeSats is because originally PSAS was really only working on rockets as well as some other projects. But along the line, this was the flight computer, right? And we realized, wow, that looks a lot like a satellite. So maybe we could try this out. So this is kind of the origin of where OreSat started. But I wanted to kind of show it because it's really cool.
So this was a rocket. This was the internals of a rocket that you then decided to base the internals of your CubeSat off of.
I don't know if I can pull it by myself.
Yes.
Oh, sorry.
Yes. And so David's grabbing the actual rocket to actually show.
And so just
And
to show
do these have standardized form factors in the same way that your CubeSat? I see. Oh, okay.
No, this is all custom. And in fact, I want to show you what kind of space hipsters we are. This was flown first time. This is not the one that was flown in 2005, but 2005, a model like this was flown, and it flew Linux. As far as we know, it was the first rocket to fly Linux. And
wow.
The first rocket to fly Wi-Fi as well. We think we're the first group to push Wi-Fi past Mach 1. And this is
ooh.
and
my goodness. I love
that's what
it.
most of your guests have, right? Just bring rockets out, right?
Yeah, I love it. This is why I love doing this kind of stream. People show me the weirdest stuff. I love it. Like, this is great. I love the fins as well.
Yeah,
so this is easier, you say, than a satellite? Because it looks to me like a lot larger and more complicated than those little CubeSats that you showed me.
So I'll give them the quick tour, and then you guys can drop it.
Yeah, please do.
So these are microwave patch antennas that are an open source cylindrical linear polarized patch antenna that we designed specifically for the rocket because it's made out of aluminum, and we wanted to broadcast off of that. This whole flight computer thing fits inside there, right there. And this was all custom built by mechanical engineers. And this is, they're called canards. You can actually control how the rocket rolls in flight. And that was our baby step towards control for the rocket. All right, go drop that thing. And
I love
so
it.
we started there, and this is everything you'd expect in a little unmanned aerial vehicle, right? It's got a lithium-ion polymer battery pack. This is a PC104 stack with an x86 processor that runs, I think we were running Linux 2.3, maybe 2.2 on this rocket. We have a software-defined radio GPS receiver that we built ourselves. Everything talks Ethernet, so that's a big Ethernet and power distribution board built by students. And then our claim to fame really is one of this, which is our communication system is just 802.11b. It's the old style Wi-Fi, 2.4 gigahertz, a megabit per second. And we power amplify it under the amateur radio regulations. And so we can get a megabit per second for the rocket, it was only 10 kilometers, but we're doing an experiment right now where we hope to get literally hundreds of kilometers from space down to the ground using Wi-Fi.
Wow.
So our joke is
that's
you can't
exciting.
get it from the basement, but we can get it from space. We have cameras, we have an inertial measurement unit, we have other stuff in here. But this was thank you, Emmy. This is a good introduction to a satellite, right? This is a satellite, except it just doesn't have solar panels, and it's in the wrong form factor. And so when we realized we built that, we thought, oh, let's build the next rocket, but let's build the next rocket with a CubeSat as an avionics system. So basically, the rocket becomes an Ethernet peripheral for the CubeSat. And that's how we started the project. And then we realized we could do the CSLI proposal and get into space, got into that. And then 2018, 19, 20 happened. And one of the interesting things that happened was SpaceX and reusable launch vehicles and space getting really cheap all of a sudden. And so now there's tons of launch opportunities. And we have many like really weird stories. And one of them was receiving an email that basically said, hey, we have an opportunity to fly something into space. Do you have anything you want to fly? And we're like, what? That's sketchy. And the answer was, of course, yes. And so instead of the 2U satellite with all the complicated stuff that we're trying to build, we said, can we do a really simple beep sat, a Sputnik, if you will? And that's the sort of pejorative term for a super simple satellite that just tests the systems of the satellite. And so that was actually July of 2020?
Yeah, June, July. I think it was like June or July 2020.
Yeah. And then we were ready to launch it within 6 months, 9 months, which is kind of unheard of. Like we could just throw it together because we've got this entire sort of Tinker Toy kit for CubeSats now. And
that's super awesome.
Yeah. And then
can I just take a moment to just say hi to a couple of the people in the chat? So Drew Festini's joined us, who says hello to everybody from PSAS. Leon Anabi has joined us all the way from the other side of the world. So hi, Leon. Nice to see you here. And then there was a question here from Katie Spivey saying, are these OreSat shirts and can we buy them? Now, I will say that at our last hardware happy hour, Drew Festini was there and wearing an OreSat shirt. And a lot of people were like, excuse me, where can we get those? So are they available? Can we get OreSat shirts?
Yes.
Or are they just...
Yes, Emmy, are they available?
That's a great question. Thank you for asking that, Katie. I actually know Katie, so thanks for the call out. But right now, OreSat shirts aren't available. Eventually in the future, we'll probably do another run, but we just need to make sure there's the interest there. It's sounding like there's more and more. And so either we'll do another run of these shirts or we'll do a different design. And
you do them during the campaign.
Oh, that's actually a good idea. We should definitely do
that. But if you
add the supporter level.
If you see the shirts out there, they do break through all of the subsystems that are here.
They're great. They're actually really great shirts. Can you stand up? One of you stand up so we can see the shirt. Look, go and stand up. But let me spotlight you. Well, yeah, look at that.
There we go.
So yeah, it's like you can't see the actual words, but you can see that it's a breakdown of all the different things that are in the shirt. It's actually a pretty cool shirt.
So yeah, one of our other mechanical engineers, Hayden, actually designed it, which was really cool.
It's really cool. It's a great shirt, and we should definitely make them more available. And Drew's also said first to push Wi-Fi past Mach 1. Okay, yeah, that's not a bad thing to assert the claim. Oh yeah, Drew also loves his OreSat shirt. Yeah, more love for the OreSat shirt. There is. All right, cool. So we've heard from the people in the chat. What are your? So we've talked about your. It's actually a question I wanted to ask. So you talked about your satellite that's gone up in space. This like 1 unit CubeSat that's gone up as a beep sat. Which you said was a pejorative term for a basic satellite that just beeps, right? Okay, so what is the basic? What would be in this beep sat? What's your baseline for a working satellite?
Yeah, so we have I guess the baseline is we have our main flight computer, which we call the C3, and then we have batteries, we have solar modules, we have some basic like telemetry on board so we can get back like temperatures, and we have a star tracker on board so we can actually read where we are in space. But there isn't. Do
we want to point at those things real quick?
Yeah, let's go through each of the subsystems.
Yeah, for sure. I've soloed you so people can see. Yeah.
Start with the solar panels, David.
Yeah.
David, do you know anything about the solar panels?
Oh God, they're horrible. So we have solar modules on board. They are gallium arsenide cells. So we have 2 cells in series, and 1 goes on each face. Each cell has its own embedded maximum power point tracker, which is kind of cool. Internal, we have the batteries, which are actually, if I can pull it out, you can't see it underneath there, but these are actually just regular 18650s cells.
Oh.
Yeah, right. So we have there are
What
four
are they? What are they wrapped in? What's that shiny metal, plasticky stuff?
insulation.
It's called MLI, multi-layer insulation. It's essentially just aluminized mylar to keep the batteries warm in case the satellite gets too cold, because we have to keep them above 0 degrees C, or they get ice, and then the batteries don't like the ice.
Oh, I see. Well, actually, we had a question saying, how do they take the cold? Someone joining here. So is cold a big design consideration for, I guess the temperature extremes must be a large design consideration for making a satellite like this.
Yeah, so we with the batteries have Kapton heaters on board so that we can actually heat them up. And so you do design around those temperature extremes, but actually for OreSat 0, it's been pretty consistent, like 22C, right? And that's just because of our orbit. We're in a sun synchronous orbit. So we're actually almost disappointed because we're not going to get to test the actual heating.
That's so interesting.
Yeah. To talk about it for just a second, it's actually the thermal concerns in space are it's one of those things you don't deal with on the ground, right? You know, get a hot processor or something like that, you turn on the fan or use a heat sink. We can't do any of that. There's no air to dump the heat to. And so if we generate heat on board, we have to get it out to the outside edges to radiate into space. And that's a really weird situation. You're out there in space. The universe is 2.6 degrees Kelvin. So it's like minus, 270 degrees Celsius, right? So it's super cold out there. But then you've got this big warm Earth next to you, which is like, 25 degrees C-ish. So you can kind of soak up some heat from there. And then a couple million miles away, there's this big 1.3 kilowatts per meter squared light bulb going off, where you get all of your power and heat from. And so if you're not careful, one side of your satellite can get up to 150 C, and the other side can get down to minus 50. And that's a real problem because I don't know if you've ever left your electronics out in a hot car or in the snow in Minnesota or northern Canada, but it doesn't work after you do that. And so you have to do all these thermal regulations, thermal tricks to keep everything at roughly the same temperature. And that involves heaters. Sometimes that involves trying to attach your chips directly to the frame. I'll show you. First of all, every circuit board we're going to show you today has maybe a distinctive color. And so shout out to
why is that?
And Lane and Drew, thank you for sponsoring OreSat. And literally, you might notice we kind of built the whole satellite out of circuit boards, purple circuit boards.
I see that. Yeah. It's one of my favorite things about OreSat. It's just so distinctive looking. I love the purple circuit boards look.
So we're at Spaceflight up in Seattle where we're integrating, right? And there's a couple satellites all out there, and we're doing ours, and we bring ours out, and everyone stops for a minute and goes, "Oh, that's really pretty." And we're like, "Yeah, it's
That's super cool.
Anyway, so here's a circuit board.
Drew's returning the love.
So here's a circuit board, right? And what you'll see is that there are gold stripes on the three sides. So this is a 4-layer Oshmark board. And what we've done is we've actually taken the ground planes and we've stitched them on the very edges right here. So if we generate heat, we have a little STM32 processor on this particular card. If that generates heat, we dump that to the ground plane. That ground plane then goes to the edge. And then, hey, mechanical engineer, tell us about the wedges.
I'm not going to be able to explain this well enough. I think you should explain the wedges.
Okay, that's fine. I can't explain them. That's why I told you to explain them. So what we have is, and I don't think you can see this, but I'll try it anyway. Inside, you'll see slots. Yeah,
we can see that.
Okay, great. And then you
can use the beauty blogger technique of putting your hand in the rest of the frame, and it will autofocus on the behind the thing. It doesn't matter. That's fine. We can see the slot. Yeah, there we go. Someone's not spent much time on beauty blogger YouTube.
You need to watch more makeup.
Andrew. Yeah, exactly.
It's just too bright.
I realized my references were incorrect the moment I said it. I'm sorry. Yeah, I love it. Yeah, we can see the slots.
So inside the slots, we also have these thing we call wedges. And what happens is, like the old 1970s card cages, which this kind of represents, right? Because you can like pull these things out. We actually have system that goes in there where I can't show it because the solar panels are on top of it, but we have fasteners on the outside that when you fasten them down, they pull a wedge in that pushes a triangle up, and it actually captures the card into the satellite frame. So those gold edges that we have in the circuit boards actually not electrically because it's anodized aluminum, but thermally couple this card to the aluminum frame on the outside.
Yeah.
That way we can dump our heat and also keep the batteries warm, all by kind of thermally coupling this, or not. We can tune it a little bit based on what the edges are and how the edges get clamped into the satellite.
Right. And we actually intentionally on the battery cards, we don't do that. So that's all rubbed out. There's no copper on the edges of the battery cards because we want to thermally insulate it from the actual rest of the
I see.
The other one fun feature I want to talk about, because I think it's kind of funky, that I'm not going to be able to talk about the technical side, but Andrew or David can. But our antenna system on here is our turnstile antenna. And if you can see there, those are measuring tapes. So I don't know if you guys want to talk about why we're using measuring tapes. A little bit of
I've seen some people making antennas out of measuring tapes before for like homemade kind of ham radio stuff. I didn't realize that's what that was. That's so cool. Are you using, tell me about the measuring tapes. Oh, hang on, wait, look. Katie even asked, have they talked about the antennas yet? No, Katie. Let me put my face.
I wonder who worked on the antennas.
We have not talked about the antennas, but the antennas look amazing.
Katie worked on the antennas, which is
I love it.
One of the things you need to know about CubeSats is that this is a really, really common form factor, and we can talk more about why that is.
I was going to ask actually how common it was. Yeah.
But one of the problems is when you go to space as a CubeSat, you get put in a box, and you can't have anything sticking out from the sort of outline of this box, and so everything you do has to stay in the box. So this antenna would not fit right in a box. So what we do is we take our antennas and we wrap them up really, really, really tight in a little spiral.
Oh.
And this is actually
so cool.
And then what you see, this is hard to see, but you'll see that center ceramic resistor. You'll see little lines going through it. That is actually monofilament line. It's fishing line. And when that resistor gets really, really warm, it'll melt the monofilament line. And then these doors pop open and the antennas just swell up.
Wow.
So these are what we would call deployable antennas. And shout out to Qorvo, because the only way that these things work is with Qorvo products in there, because they're not the best antennas, but they're really great. They're omnidirectional. We've got UHF at 400 megahertz, L-band at 1.265 gigahertz, and then an L1, which is GPS. And so these guys are how we talk to it.
So we said that so WW Walk, I'm not sure if I'm pronouncing your screen name correctly there, said, yeah, they're like DIY Yagis, which is what I was thinking of, the DIY antennas that you see. That's super cool. And he's also saying about loving the old slots. So he's saying, yeah, that looks like the old computers with the card slots. That's really cool. Compliment as well, saying what a nice and simple deployment mechanism. I definitely agree. Okay, we also have a question from David Anderson saying, yeah, did you do any vibration testing to verify the mechanical design?
Do you want me to? So yeah, we do vibration tests for all of our satellites. We work with the awesome group out at Tektronix, and we get to the vibration table out there, and so it is very fun and very loud, and we get to see and hope that nothing falls apart, and so far nothing has. But it's a great way to kind of test exactly with our deployables to make sure that everything's holding tight. I will say it is a very simple and cool design, but I like putting it together and assembling it. I feel like a surgeon because we have a bunch of like things that we're wrapping around and it's crazy. But yeah, we do vibration testing.
That's really awesome. And when you put the antennas inside, that must be a really, really fiddly job to, I mean, do you is it you doing it there? That's some serious hand-eye coordination that needs to happen in order to create that. Do you feel like you're making a trap?
A little bit. There's a couple of us that do it. We've got two folks that are really good at it, but usually you need a couple hands. It's kind of like tying a knot. You have one person putting their finger down and
Yeah.
now around. But yeah.
And David had a follow-up question actually about the vibration testing, which was how many G's were applied? Do you know?
Oh, ask me. Thanks. 10. So what's really interesting is that when you might not know, unless you've got a satellite in space, that when you go to space, you have to do tests on your satellite. They really get mad at you if your satellite falls apart during launch and make damage the rocket, right? So you have to do a bunch of stuff. You have to put it in a vacuum and outgas it to make sure that stuff doesn't come off when you go into the vacuum. You have to go through vibration testing, and they give you what's called an EVP, an environmental verification plan. Yeah, okay. And the EVP says, okay, it's 10 Gs, but it's 10 Gs over the spectral content. So they actually have a sort of spectral diagram of where the random vibration takes place. And you do it 3 times in X, Y, and Z, and Z. And then you,
thank you for the translation.
and then and you do it for a minute. And if you go with a smaller, more intense rocket, you could go up to 12 or 13 Gs. If you're going to the ISS, they literally put you in bubble wrap and it's like 3 Gs. And so you've got different vibration test plans depending on how you go up.
Wow, that's really interesting. And do you do much of that yourself, or is it very much like you hand it off to the professional in the lab and you come back and get your results later? Like, do you get to watch and press the buttons, or? Like...
As I hate to use the word shout out too many times, but one of the things that
go ahead, please.
that really you need to know about this project is we are not funded. We're crowdfunded, and these guys are the people raising the money. And as a poor open source engineering project, we really appreciate people reaching out and helping with in-kind donations and in-kind services. And so Chris at Tektronix reached out and said, hey, we've got a vibration table that we vibrate our scopes for quality systems for. Do you want to use it? And we said, oh my God, yes. And so we go there, we hand it to him. He puts it on this giant, it looks like a solenoid, giant table with a big that vibrates. It's like the world's biggest bass speaker, right? It's all electromechanical. And then he spectral content in, and then we kind of bolt it down to the top of the table, and then we quietly weep to ourselves as our years worth of work is shaken at 10 Gs right in front of our eyes. But so far, nothing has failed. So
that's fantastic. It's particularly since you've been doing it on a shoestring budget, it sounds like.
Yeah.
Have you? Yeah, that's pretty exciting and inspiring to hear you've done it on such a small budget. I'd be really interested to hear if what you've gotten and what you've given from the open source community. So obviously you probably based some of your designs on other people's prior work, but I'm wondering if other people have reached out to you and let you know that they're using your designs or that they're using your firmware or so on as well. Like what's open source brought to your project?
A lot. That's so like every other open source project, shoulders of giants and all those catchphrases, exactly. Right? So really, I'd say ChibiOS, which is a real-time operating system for STM32s, Linux for sure, the whole Linux infrastructure for embedded systems. CanOpen, which is not really, it's more like a standard than it is an open source thing, and all the little
CAN as in like CAN bus.
Yeah, sorry, controller area.
Yeah.
Use on the satellite. Gosh, what other open source things have we used? We just recently switched to KiCad.
Oh, you did? It made a lot of improvements. I'm thinking about doing the same.
Strongly recommended. We used it for a long time, and then unfortunately, Autodesk turned Eagle into a Windows-only platform.
They did.
And we support Linux really strongly, so we couldn't use it anymore, and so we switched to KiCad. And with version 6, we're super happy. It actually is. It's a solid CAD system.
That's great. That's great.
Git and GitHub and all that. We could not have done this without Git.
Have you had other people use your stuff? Have you had other people take from you?
want to talk about that?
Yeah. So there is a group of other universities using our designs as part of a larger mission, as well as they're using some designs from other schools. So Cal Poly Pomona and Stanford and Hawaii Space Flight are working on a mission that is vaguely using some of our hardware. I believe there's some other groups that have reached out about our designs. I don't know.
And how does that make you feel good as an engineer, knowing that your designs have got a life outside of your own workflow?
Yeah, I mean, it's really satisfying to see other people take the work that we've done, or that I've personally, like PCBs that I've personally designed, like show up in the wild sometimes. It's really satisfying, and it's always fun. Like, hey, I know what that is, kind of stuff.
That's really awesome. That's a great feeling. We've got Drew says hooray for KiCad, and Leon has said well done for using open source tools, a sentiment I definitely echo. We've also got another question from www.org. Is there something special about soldering stuff to send into space? Actually, that's a great question. Do you just use normal techniques, or do you have to use special ways of keeping your electronics in place?
We use massively parallel neural networks called undergraduates to solder all of our space stuff.
Is there anything different about the technique?
If the mechanical engineer gets to solder, then it's not that special.
One of the things is we do use leaded solder just so we don't get like tin whiskers in space. That is a thing. And you need to clean the boards thoroughly. Just make sure, clean off all the flux. You need to be pretty paranoid about that. But in terms of like the actual soldering itself, I mean, you do it carefully, but there isn't really anything that special about it, about what we do.
Okay, cool. Useful to know. And interesting that you use leaded as well to prevent some things. Now, okay, I really want to spend some time talking about, so you've got your satellites up in space at the moment, your first ever test. What kind of what functions are going to be different moving forward? So you've got another 2 on the docket lined up. You've got one that's going to be, so at the moment you've just got a one, and you're doing a 1.5 and a 2, is that correct? So what functionality is going to be different? What can we expect to see from Oregon's next satellites?
So right now, our satellite is tumbling in space, and there's nothing we can do about it. We don't have propulsion, and we don't have something called attitude control.
Oh,
perfectly fine for us. However, the next test is attitude control. So OreSat 0.5, which we call it, has these things, which are called reaction wheels. And Emmy will spin one of them, I think.
Solo that. Nice. Oh, I see that. Yeah. And what materials are those? What's that made out of? Is that metal? Oh, yeah. Nice.
So those are teeny tiny little drone motors where we've taken the bearings out and replaced them with hybrid bearings, silicon nitride bearings, because metal to metal contact tends to bind in a vacuum. And so they're just drone motors with big brass wheels on the outside. And if you remember back to your high school physics, conservation of angular momentum, if you're sitting there in space and you spin something up, then the rest of your system rotates the other way. And so 0.5 is to test our attitude determination and control system. And that, or ADCS, and that is probably the hardest thing that we will have done yet. That is a really complicated system. It's control and feedback, and lots of things can go wrong. You need a star tracker, which is a camera that grabs the star field and tells you which way you're pointed. You really need a GPS receiver to tell you where you are in orbit to a larger precision than you can get from just the ephemeris, which is the orbital data you get. And you need a gyroscope to make sure to know if you're spinning or not. There's lots of things you need, and then you need to control those 4 motors. You really only need 3, but we use 4 so one can fail, to control how the satellite points.
That's really, really interesting. And I've not seen the wheel method before. I've seen kind of compressed air propulsion methods before, open source stuff. I actually visited, do you know the Copenhagen suborbital people? I actually visited their lab when I was in Copenhagen. And I saw their compressed air propulsion systems there. That's the first. So these wheels are really interesting. And you use 4 of them, is that correct? And where are they positioned on the board? On the on the satellite?
Do we have a 1.5 view? No.
I don't, not assembled.
Okay. Right in the very center of it, you can kind of see in this, there's a little bit different pattern right in the center than there is.
Yeah, I see that.
Yep, and that's where we put the reaction wheels. The other thing we put down there are in that center are called Magnatorquers. So not only do we have the reaction wheels to do pointing, kind of precision, fast pointing, but since we're up in space, we've got the Earth's magnetic field right next to us. We can actually just spin an electromagnet up and torque against the Earth's magnetic field, magnet to magnet. And those are called Magnatorquers. And using 3 of those, which Emmy's trying to find, I don't know where they are, actually. It's funny. They're not on the table right there? Oh, weird. Okay. Then we can actually also much more slowly control how the satellite points. And then just to get all technical, because it's kind of interesting, there's a difference between those two systems, which is weird and physicsy, which is that the reaction wheels, no matter what you do, you can't change the conservation or the angular momentum of your system. So we can spin up and we can spin down and stuff like that, but we're always going to eventually come back to where we were. The Magnatorquers are torquing against the Earth's magnetic field, an external force. So we can actually change the angular momentum using the Magnatorquer. So one of the things, going back to thermal control, one of the things that we really want to do is spin the satellite, right? One of the things we didn't tell you is there's solar panels on the outside, but there's no solar panel on the top or the bottom. So if the satellite is rotating and you're the sun and it's like this, we're toast because there's no solar panel there. So what we want to do is rotate for thermal reasons, but like this, where all the solar panels are always in the sun and we're distributing the heat of the sun around the satellite. So that's what Magnatorquers is, that sort of inertial state control.
Very interesting. Thank you for explaining that. Okay, so I did want to talk a little bit now, seeing as we've already been talking for 40 minutes, inexplicably somehow, it's gone very quickly. I wanted to talk a little bit about your upcoming plans, including the crowd supply campaign that I know you're planning to run this summer. Tell us a little bit about this. What are you planning on creating?
So I think we have to tell you about what we call the OreSat Live mission, which is the 2U CubeSat Launch Initiative mission coming up sometime late this year, early next year. Yep. We've got 2 missions for that satellite. We have a climate science mission using a shortwave infrared camera that we're not going to talk about that looks at cirrus clouds. But OreSat Live is the other mission. And OreSat Live is adorable. Do you guys want to explain it?
No.
All right. So one of the things is, again, with the rockets, right? We've always been using Wi-Fi, and we've gotten Wi-Fi past Mach 1. We've done it from hundreds of kilometers. What we'd like to do is we'd like to take that to the state of Oregon. And when we were doing this sort of first satellite for Oregon, we thought, how can we reach out and get everybody in the state involved? And we realized that we could do a kind of a silly thing, which is if we put Wi-Fi on the satellite, and if we had a zoom camera, a telescopic lens, and we had 802.11 and a very high gain antenna, and if we could point the satellite, then when you're in Oregon, we could point the satellite at you and kind of point and stare as you go over. And so we could broadcast video signal, and then Oregon high school students, like not Emmy, could build.
What are you holding there, Emmy?
Yeah, so I'll talk a little bit of this. So this is a handheld ground station. So this is what high schoolers would build to be able to talk to this, talk to the satellite. So this is a little bit of an older version, but essentially they'd be able to use their phone and be able to make this out of a pretty cheap 3D printer and make all these parts. So that way they can hold it up and see what the satellite sees. The kind of funner version of this system is called the selfie-stick from space. And so that way they can see themselves from the perspective of space.
So the high school students will actually give us their lat long in Oregon. We'll point the satellite at them, start streaming live video. They'll use this thing to actually download the video and get live video.
Wow. Wow, that's amazing. And how close, I mean, is this something that you'd like to have working, or is this something that you're pretty confident will actually work with with your third satellite?
Huh, that's an interesting question. That's why we're doing the first 2 satellites. We're most afraid of the attitude determination control system. That's the hardest thing to do.
Mm-hmm.
Once that works in the second satellite, this system will just work. We've already proven all parts of the system. And so it's really just about tuning it and getting it to work. Why don't we show the thing? So when we're talking about ground supply,
show us this thing.
we actually, let's show them the ground station for a second. We expect the students to 3D print the antenna form and wrap around the wire to do the helical antenna, which is about a 12 dBi gain antenna. And then we're going to give them a kit with a circuit board and a bunch of stuff in it, including a Raspberry Pi Zero and a USB to a Wi-Fi adapter and some Qorvo LNAs and things like that. And that all gets shipped out from Crowd Supply. Thank you, Crowd Supply.
Well, it's thank you, Mauser. We don't touch it anymore.
Excellent.
Thanks, Mauser.
That goes to all the Oregon high school students who are interested in working with us. And this has all been crosswalked into Physics First, which is freshman level physics.
Nice.
So this can be done as a class project, not just extracurricularly. So we expect.
That sounds real fun.
Yeah. So they'll build the kit, give it a test, and then schedule a pass with us. And then we'll actually give them live video from space.
That's incredible. That would have blown my mind when I was 17 years old. All right, I got another question here from. I've been given the permission to just call them Walk, which is much easier than saying Walk. I'm saying I've seen one glass piece telescope for small sats on YouTube. And what will you use for a lens?
So sorry, go ahead.
Yeah, no, go on. Yeah.
Okay. So if that was Huygens optics video, that was actually our lens. So yeah. So it's a monolithic Schmidt-Krasegen telescopic lens. Like this big. Yeah. Andrew's gonna go find it. We get it's like 6 meters per pixel on the ground. So about 6 meters per pixel on the ground. It is hand ground by a friend of ours in Europe. So that is, it goes onto the card here. So this is the actual, the space segment card. This is engineering unit, hence the, mod wires.
Did you say that lens was ground by a friend of yours in Europe?
Yes. Yeah. He's one of our contributors. It's Rick, right? Richter Horst.
Shout out to Richter Horst. Thank you for grinding the lens.
Yeah, it's literally in his garage, right?
Yeah. He has it.
Wow.
Yeah.
What country? Do you know?
The Netherlands.
Oh, that makes sense.
So
nice. Okay. Oh my gosh! Wow.
So this is a 3D printed holder for it. I shouldn't do this without gloves on, but I'm going to anyway.
Wait, I think this Walt person is enjoying it. Oh wow, that's a masterpiece. Look at this. I love it really so much.
And this was again hand ground by Rick in the Netherlands. We love Rick because he's hilarious. Yeah, he not only works on the world's smallest Schmidt-Casagrins in the world, but he also works on the European Extremely Large Telescope, which is the largest telescope in the world. We just love the fact that he works on both of this.
What a dude. What a dude. Yeah. Shout out to Rick. That's so amazing. Also, with that last comment, Walk, you have become the winner of this week's box of mystery hardware, including a bunch of exciting Qorvo stickers, a bunch of Qorvo enamel pins, which are really cute, this Qorvo bottle, which we love. And what else have we got in here? We've got, oh my goodness, loads of stuff. Some stuff from Adafruit with some microcontrollers. Let's have a look what we got in here. Maybe I'll open it. I can't open it. We've got a Mauser hat. We've got, which is always very fetching. Here we are. So plenty of swag and lots of electronics in here as well. So that'll be winging its way to you. If you can send me your real name and address on Twitter and by DM, I will get that sent out to you in the next week or so. So please let me know who you are, and we will sort you out with that. So thank you for commenting. Okay, carry on. Is there what else did you want us to tell us about? Because I'm conscious we've only got about 10 minutes left. What else? What other information did you want to jam into our minds before we leave?
I just want to point something out. So I helped design this mounting system with Rick. And one of the things that we talked about, kind of the impact of like being able to see open source and see the designs we're using being used by other schools. But one of the really cool things about PSAS is that it's been around for 20 years. And so a lot of these projects, a lot of these works is building off of other students. So since Katie's on the call and she called me out for shirts, I have to call her out now. I took over this system from Katie. And so it was really cool being able to see all the work that she did and then be able to continue on with it. And now as we're getting ready to graduate, we're able to kind of hand off what we've been working on to another group. So it's a really great opportunity to kind of be able to say, okay, I learned this stuff and it's super cool and kind of crazy, but like, let's see if we can get someone else on board and see if they're interested. So this is a small thing. If you're interested in open source aerospace and you want to check out a cool group, we'd be happy to have you. So that's my small speech.
That's awesome.
Really important. Not only do we have students, but we actually have some high school students who work with us. And have lots of industry advisors, people who come in from local industry who help out with this, because I mean, these guys are great and we're going to cry when they leave. But there's a large amount of time we spend training folks. And so having people who already know what they're doing coming in and mentoring students and working with students is a huge part of the Portland State Aerospace Society. And it's really fun because you get to have your own satellites and rockets and things like that. So strongly recommend, if you're at all interested in aerospace and engineering and systems level engineering, to come out and play with us here at PSU.
Drew's asked, can anybody join PSAS, or is it limited to faculty and students?
Nope, literally anybody.
Anyone can join over 16.
Yeah, that's right.
Okay, yes. Anyone over the age of 16 can come and help you make satellites. And do you still make rockets, or is it satellites only now?
I hope we still make rockets. Otherwise, my capstone is toast. Yeah, we still work on rockets. I don't think you can really see it, but behind us, there's a one-to-one diagram of our future rocket called LV4, and that will be about 25 feet-ish long. And then we also hopefully will be launching LV 3.1 this summer. So if you want to go and be cold in Brothers, Oregon, or be really warm because there's a lot of temperature changes out there, we'll be launching a rocket out there as well this summer.
That's so exciting. And a follow-up question from Drew there. How do people find out more? Are there meetings people can come to? Do people like to have to follow you on Twitter? Like, what's the way for people to find out more about you and for people to get involved?
You can totally follow us on social media. That'd be cool. But if you don't want to follow us,
what are your handles? Drop your handles. I'll put them in. I'll put them in a. You should.
At PDX Aerospace.
Most of the PSAS ones are.
I like that question mark.
Most of them are at PDX Aerospace. If you also go to our website at pdxaerospace.org, we have a great link there that has how to get involved. That kind of walks you through some basic things about aerospace, and then when our general schedule is. On our homepage is our Google Calendar, and all of our meetings are hybrid, so you can either join.
What was the URL again? Sorry, I'll type and bring it up.
pdxaerospace.org, and then there's also OreSat.org, which is about our satellite specifically.
Okay, but you can get to the OreSat stuff from the aerospace one. I'll just make it into a banner. Carry on talking. I'll bring it up.
Oh, yes. And so on the bottom of our homepage is our Google Calendar. And on there, we have Zoom links to each of our meetings that you are welcome to check out. We have, oh, that's so cool. We have general meetings on Tuesdays at 7 p.m. And then for our OreSat meetings, we have general meetings at 2 p.m. on Fridays. And anyone is welcome, and hope to see you there. Yeah.
And a specific shout out to people who do embedded Linux. We're now in, you get your hardware done, and then you get your initial bring up done, and then you try and get all of your functionality done. And that's when you realize you needed 2 years and a fleet of programmers to get stuff done. So we're particularly interested in industry advisors, and people interested in working on embedded Linux projects.
Embedded Linux projects. Okay, we will put the word out there. Consider people requested. Amazing. Okay, cool, fantastic. I've got a couple more questions here. So Leon's asked, oh, this is probably a terrible question. Is the global chip shortage having a big impact on the aerospace industry and on this on these type of projects?
Fine.
Everything is fine. Why do you ask? Yes, it's been horrible, especially because in the amateur aerospace world, like, because we can't afford aerospace grade parts because it's like $2,000 for a Mega 328 that's aerospace grade. So we use automotive grade for a lot of stuff, and automotive grade has been one of the hardest hit things by the chip shortage.
Yeah.
So yes, it's horrible. There's been plenty of times where we've had to respec a part at the last minute because it just doesn't exist anymore. The entire satellite is built around STM32s, which are impossible to buy, and we have a backstock that we're very careful with.
Lock and key.
Yes.
Yeah, I did notice the Raspberry Pi Zero on the ground station. I was like,
yeah.
Hopefully we'll be in space after the chip shortage is not a thing anymore.
Oh, when's that going to be? Because I'd love to know.
Soon, right?
Yeah. No, and depressingly not. Like nobody has any hope. Unfortunately. No, it's yeah. Well, I'm glad to hear that you've been struggling along anyway. Have you heard of there's a site called Excess Components where you can do component swapping for small projects. You should check that out. It's done by someone from the car hacking village, I believe, at DEF CON. Yeah, it's just XS and then components. They often have like, cut tape level of components rather than, a whole reel or whatever, but it's worth taking a look anyway.
Oh, thank you.
Again, yeah. I mean, they don't always have something, but it's a one place to go look for little things.
Yeah.
So yeah, I'm sorry to bring up the chip shortage, but I'm glad to hear it's doing. You're doing okay. You're doing okay anyway.
Yeah. I think
has it really? Yeah. And how has? Because you, Annie and Andrew, you're both students at PSU, is that correct? And you do this, you both. Sorry, Annie. Yeah. So do you? Sorry, Annie and David is what I meant. Not Annie and Andrew. It's because it says Emmy, David, and Andrew on your thing, and I know which one's Andrew. I've met Andrew many times before.
I don't.
But my brain was my brain doing. So Emmy and David, how are you planning to continue working in space? Is this very much like something that is setting you up for a future career, or is this a hobby that you want to go into more generalized engineering?
Yeah, I mean, I think both of us are continuing into aerospace after we graduate. We both have jobs going into the aerospace world after we leave. Although it's kind of a great primer, even if you don't want to, because aerospace has a little bit of everything. So it's a great like boot camp for engineering in other worlds, especially as an electrical engineer. Just because it's electrical engineering where you have to think about things that aren't electrical engineering. But yeah, I'm going into aerospace. I love the industry and hope to continue working in it after.
Yeah, I'm the same as David. I'm getting into aerospace after graduation, and I'm excited about it. Yeah.
So we don't have an aerospace department, right? We just have electrical, computer, and mechanical.
Oh, I see.
35 people in aerospace right now from the experiences they've got here at Portland State Aerospace. Mm-hmm. These guys got sucked up right away. They're not bragging. They should totally brag. In fact, they're jerks.
Yeah, they should.
Yeah, well, they're supposed to spend the summer with us, bringing up the next generation of kids. But no, they have to go get industry aerospace jobs and build other people's satellites. Fine.
Good for you. Good for you, both. Pleased to hear it. Although I'm sorry for your loss, Andrew.
Thank you.
But there's always next year's student.
That's right.
Yeah. Next round of undergrad.
All right, well, we are somewhat improbably at 12:59, so that means we are signing off. I hope to see some of you at least on Tuesday at the in real life hardware happy hour. I know that we owe you a drink or two for putting Oregon's first satellite into space. Space heroes, congratulations. Thank you so much for joining me today. Have you got any last shout outs that you want to give, or any last requests for information, or are we all happy to
we call it NCAP.
Use your words. Okay.
Thank you. Yeah, we want to do a general shout out to the people who helped with OreSat 0, Oregon's first satellite, and we actually have a plate. Let me grab one. Yep. All right, great. That we just want to show you as we sign off.
I had to find the non-redacted.
Please do. Oh, hang on, let me spotlight it. I love it.
So she flies with her own wings. That's the Oregon State motto. And thanks to
Is that really?
Yeah, it is. Most people don't know that.
Oh,
which is funny.
I've seen that around places, and I was like, what is it?
So thank you to Osh Park and Spaceflight and you at Crowd Supply and FLIR and IEEE and IAA and Oregon NASA Space Grant, all the folks who've helped us. And just to show it off, these are the folks who helped build and fund the satellite. So we've got some names in space of folks who helped out. So thank you all for helping us get into space.
So. What a lovely gesture to the people who've helped you along the way. And of course, yes, as you said earlier in the stream, open source space is very much standing on the shoulder of giants. And thank you for opening up your work so that other people can stand on your shoulders too. It's a really exciting project, and I'm very, very deeply happy that Ground Supply gets to be a little part of it. So thank you so much. Just a couple of things before we sign off. We wanted to say, Leon said, thank you for the amazing talk. PSAS, keep on the amazing work. Walk said, thank you. Jeff Meisner said, beautiful work. Congratulations and keep up the good work. And of course, Drew says loves the PCB artwork as well. So thank you so much for sharing your work with us here today on the Teardown stream. You've shown us so many amazing things. We've seen rockets, we've learned about temperature control on PCBs, we've seen inside what a CubeSat looks like. It's been really, really fun. So thank you for sharing your knowledge and expertise with us. As for the rest of you, I will see you in 2 weeks from now when we're going to be starting new streams on lots of topics next month about Python on hardware. So we're seeing some really exciting people there. We've got stereo Pi people coming, and we're going to be lots of fun things there. So next month, all about Python on hardware. We'll see you next time. Thank you for joining us, and I'll see you all soon. Bye.